Next, we're going to talk about higher order derivatives. And to do this, we're going to return to our bottle example. So let's say that we have a bottle on the left, and we want to draw a graph of the height of the water in the bottle as a function of how much water we've put in the bottle. So really the volume of the water in the bottle. And we see that for this initial bottle, as we add increasing units of water into the bottle, the height is going to increase at a steady rate until we get to this neck of the bottle. So for this first part of the bottle, as I add water into the bottle, the height is going to increase at a constant rate until I hit the neck of the bottle, and then it's going to increase faster because there's less width here, means that a smaller amount of water is going to make the height of the water increase at a faster rate. Now let's look at a different bottle. So this is supposed to be a perfectly circular bottle. My picture's a little funny because I'm not very good at drawing things. And let's think about what happens to the height of the water in the bottle as the volume of the water increases. Notice that I can think about sort of taking slices of equal height along this bottle. And we see that initially a small amount of water is going to increase the height more rapidly. And then around the midsection, the same amount of water is going to increase the height more slowly because it's fatter through this region. So that means that initially I'm increasing faster, and then I'm going to increase at a slower rate, and then up at the top, notice again it's getting narrow again. And so just like how up in our first bottle, when the width was narrow, our volume increased rapidly, here the width is narrower, and so my volume is also going to increase more rapidly. What does that mean in terms of the graph? Recall that we said that we're starting out by increasing rapidly and then increasing a little less rapid and then increasing rapidly again. So my steep slope is going to indicate a rapid increase, and then sort of a less rapid increase, and then a rapid increase again. So approximating this graph, and we see right at this point, this is a point that I want to point out, the instantaneous rate of change at the neck of the bottle is going to be maintained through the rest of the neck, meaning that my rate is increasing, 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 and then it's holding at that same rate through the rest of the neck of the bottle. So that's going to be indicated by this straight line through here. This is increasing, increasing. So why are we talking about this? It's bringing up two different ideas. One is the idea of rate of change, which is what we've talked about before, because my rate of change, in fact, I'll just say the instantaneous rate of change is going to be the slope of the tangent line. And that's asking, so for a 1 unit increase of water in the bottle, how is the height increasing? But the thing that we're really interested in these graphs is something a little more beyond that. We're talking about how much is the rate of change changing. I'm looking at the change in the rate of change. Because we were talking about here we have a faster rate, here we have a slower rate, and here we have a faster rate again. And our change in our rate of change, we have one word for that, and that's called acceleration. Typically, we reserve our term acceleration to be talking about the change in the rate of change of distance or the change in velocity. And we have the general way that we describe this is going to be our second derivative. The change in the rate of change is our second derivative. So let's summarize what I just said in a sentence. So we say that the second derivative is the rate of change of the slope of the tangent line. And we can think of this graphically in a couple of different ways. So if I have some function, here's my function f of x, and let's say I have a function and it looks something like this. I'll grab a red pen to talk about tangent lines. So before we've talked about rate of change, and rate of change is looking at at a single point on this graph, what is the tangent line? The second derivative goes a step beyond that, and I want to know, how does the tangent line change as my x values change, essentially? And we see that on this graph, the slope of my tangent line, it starts with a positive slope, and then it has a less steep slope, and then here it has a slope of 0, and then here it has a negative slope. So my slopes are going from being a positive slope to 0 to a negative slope, meaning that the change in the slope of the tangent line is getting more and more and more. First it's getting smaller and smaller, and then more and more negative. So my rate of change of the tangent line you would expect to be negative in this case. Whereas, let's consider a graph in the opposite direction. We'll call this graph g of x and our function x. So for example, if I'm thinking of this as a time versus distance graph, again, our rate of change is given by the slope of the tangent line, but our second derivative is measuring how is my tangent, the slopes of these tangent lines changing. And here, our slope started out pointing downwards, being a negative slope, meaning my velocity in this case was a negative velocity. But my velocity levels out and then grows faster and faster and faster. So in this case, my second derivative would be positive, because my slopes start out negative and they become positive. So how is my the rate of change of my tangent line changing? It's changing in a positive direction. Unlike, maybe let's just go back to our bottle example. And this initial bottle, at least through this part of the graph, we see that the slope of the tangent line isn't changing at all. So the second derivative in this case is just 0, because there's no change in the slope of your tangent line. All of your tangent lines are exactly the line itself. So that's sort of a conceptual, graphical way of thinking about what the second derivative is. Let's go ahead and look at a numeric way to be able to evaluate second derivatives. And we'll start by looking at the notation. So if we have some function f of x, our first derivative is f prime of x. And you know what? Second derivative is exactly what you want it to be. You can just start adding dashes up top here. And there's an eventual point where there are too many dashes to be able to read really legibly. And so it's commonplace to be able to convert over to little i's. So after the third one of these, it would get really hard to be able to recognize how many derivatives it is. And so for the fourth derivative, I might just write a little 4 up here to mean that I am taking the derivative 4 times, rather than having to write out dash, 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 or prime, 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 prime. But let's say I didn't want to use this notation, I wanted to use Leibniz notation. We can also do that this way. We have our original function f of x. This is a little messy, so we have our first derivative, df dx. Our second derivative, we want to differentiate. It's not actually a fraction. We aren't actually squaring anything. These 2's are just telling us that we're taking a second derivative. And we put the 2 on the inside, on the outside, in part, I think, to denote the fact that I'm not like squaring this derivative. If I had them all on the outside, it might look like, or this might be x squared, and that's not what's going on. This is just the second derivative notation and the third derivative, and we would go on by adding 4's or 5's or 6's. And conceptually, it makes sense that if this is our derivative, taking the derivative of our derivative is asking, well, what is the change in our derivative function? And let's look at how we could evaluate this numerically. So for example, let's say I have a function given by f of x is equal to x to the 5th minus 4x squared minus x minus 2. Let's say I want to take the 10th derivative of this function. Let's just start by taking some derivatives and see what happens. So when I take my first derivative, it's exactly what you think it should be. We're going to use power rule in this case. My 5 comes down in front, and I'm left with 5x to the 4th minus the 2 comes down in front and multiplies by the 4, so I get 8x the derivative of x, this is a linear function, so there's a hidden coefficient out front of 1. The slope of that is exactly equal to 1. So I get plus 1. And the derivative of the constant just becomes 0. So this is our first derivative. That's a review. So how do I take the second derivative? Really, I just pretend that this is a new function, and I take the derivative of this function using power rule the way that we would expect that we would. So this 4 comes down in front, and I'm left with 20x cubed, and this constant, this becomes -8 because this is linear, and then my constant term just disappears. So notice that as I'm taking my derivatives, it actually gets easier and easier because these terms keep dropping off, that anything that's a constant goes to 0, and then I don't have to deal with it anymore. And as you take successive derivatives of polynomials, it will always be the case that eventually, after enough derivatives of these types of functions, polynomial functions, you'll end up with a function of 0. Let's see how long it takes in this case. Let's do power rule again, and I get 3 times 20, which is 60, x squared, minus this 8 just becomes 0. I shouldn't have written a 0 there, but you know, it just clarifies. So now we're on to our fourth derivative. And the 2 comes down in front, so I'm left with 120x with no power because 2 minus 1 is 1. And then finally, when I get to my fifth derivative, I'm left with just 120, and by the sixth derivative, the derivative of the constant is 0. So for polynomial functions, we see that taking successive derivatives makes our function get smaller and smaller and smaller, and well, smaller and smaller is maybe the wrong word. More and more successive terms are going to go to 0, and eventually we'll end up with 0. And it's always the case that how many derivatives will it take? It'll take one more derivative than the largest power of your polynomial. Let's look at another example. It's not always the case that successive derivatives will make your function go to 0. So, for example, if I have the function g of x is equal to maybe 3e to the x, recall that the derivative of e to the x is e to the x, and so this is an example of a function that as I take successive derivatives, this function actually doesn't even change. The first derivative, the constant goes along for the ride, and the derivative of e to the x is e to the x. The second derivative is also 3e to the x, and the third derivative is also e to the x. And if I wanted to write it, one way that I could notate this is to say that I could take n derivatives, any successive number of derivatives that I want, and I will always end up with 3e to the x as our derivative. This is a generalized notation for what it would mean to take the nth derivative of a function.